Our last special segment in triangles is talking about angle bisectors and their point of concurrency called the incenter. An angle bisector, oops, I got a little ahead of myself, so ignore that circle for a minute. An angle bisector is a segment that bisects the angle in a triangle, cuts it in half. All three of those segments are called angle bisectors. Those 3 points happen to meet at a special coordinate as well. That point is called the incenter. So angle bisectors meet at what we call the incenter. Now, the thing about the angle bisectors you have to know is, now I drew a circle there. That circle is a little bit too big, so I'm going to retool this problem here in a minute. All right, now the angle bisector, they cross at the incenter. That point does have a special relationship with the triangle also. The reason it's called an incenter is because it actually is the center of a circle. It's just that the circle's inside the triangle. If I were to go from that point straight to the side of the triangle, if it were drawn a little bit better, you would see that all 3 of these segments are going to be the same length. That point is what we say equidistant to, not the vertices, but the sides of the triangle. So if I were to imagine a circle inside the triangle, it is the center of a circle inscribed of a triangle. So when you see the word in center, it's a point that's in the center of the inside circle of the triangle. Let's take a look at an animation again. In that point, no matter where I put my vertices, you'll notice that that circle is always going to be inside of the triangle. Whether it's obtuse, right, or an acute triangle, that circle is going to be housed inside of the triangle. That point is always going to be the same distance away from the sides of the triangle if I were to go at a right angle. So it ends up being that segment from the center to the edge of the triangle is the radius of the circle. Let's look at some other things on the diagram. So an angle bisector is a segment that bisects. Again, bisects means cut something in half. The vertex of a triangle. You're going to notice that these segments are the same degree. These, not these segments, these angle measures. So that's going to be an angle bisector. When those these three angle bisectors meet, they meet at a point called the incenter. It's the point where all 3 angle bisectors meet each other or are concurrent with each other. Couple key features of that. The angle bisector that forms the incenter, that point incenter is equidistant from each side of the triangle. So in other words, this point right here is the same distance from there, is the same distance from there, is the same distance from there. All 3 of these segments are the same. So you can see how you have these right angles down here. Those are the same length. Those are all a radius of that circle. So it's equidistant from the sides. It will always be the center of an inscribed, inside drawn, inscribed circle. The incenter is always inside, a lot of ins here, inside of the triangle. So let's see about how that all works. These are all going to be a radii. Means these are all going to have the same measure. You're going to have some right angles. All the angles are going to be bisected from each other. And a couple other relationships you may or may not realize. Relationship number 1 is you're going to notice that CD and CE are actually the same length. You're going to notice that AF and AE, those are the same length. And you can probably guess the other one. The other one's going to be these 2 over here. So that's just kind of a bonus part, right? Something we kind of discover as we make this triangle here. So those are the relationships we're going to work with here. These three are equal, those two are equal, those two are equal, those two are equal, and these angles are cut in half, therefore allowing us to get a lot of different things. But let's focus on this question. We got a lot going on in this diagram here. We're going to do this in a couple sections, okay? So for part one, let's focus on the angles first. I want to know what the measure of angle ABG is. The way you read that is you trace A to B to G, and you look at the middle letter. That's the angle we want to find. Now, if you look at the angle directly next to it, you'll notice that it's marked at 20 degrees. Well, in an angle bisector, those two angles are congruent, which means those are both going to be 20. So angle ABG is also 20 degrees. Let's go down here to angle BCA. That's the next angle we want to find. Notice that they give us the half of that angle. They give us that this is 11, which means that side, that angle is going to be 11 degrees. So angle BCA is actually just going to be 11 times 2, or 11 plus 11. So that's going to be 22 degrees. Remember, when I'm tracing an angle, it's always the middle letter that defines your vertex, B to C to A. Let's look at angle BAC. Angle BAC is this whole entire angle. And I don't know that angle yet, but I do know that this angle right here is 22. I know that angle ABG is 20. So if I know these are both 20, then 20 plus 20 is going to add to 40. So I know that that angle is 40 degrees. So if I want to know this third angle in a triangle, can you think of something that'll help you get the missing angle? What do all three angles inside of a triangle add to? That's right, they add to 180. So all three angles in a triangle add to 180. Which means we can actually just add these together and subtract from 180. 40 plus 22. And then take that away from 180, and you'll have that 1 degree down here at angle A. So 180 minus 62. 180 minus 62 is what? 118. So that's going to be 118 degrees. Meaning angle BAC, the entire angle from B to A to C, is 118 degrees. And then finally, angle BAG. BAG is going from angle B to A, but it's going this route here. Notice going right to the incenter. Well, because that's an angle bisector, you should realize that those two angles are congruent to each other. So I can get angle BAG by taking this angle at 118 and dividing by 2. So I'm going to take that 118, cut that in half. Use your calculator if you need to. That's going to give you 59 degrees. So both of these are going to be 59 and 59 degrees. And now I have all the angles, 59, 59, 20, 20, 11, 11, and then 22, 40, and 118, all adding up to 180 degrees. We're going to do number 6, part E, F, G, and H on a different diagram. So I'm going to redraw this real quick. Always, if you can, take the time to redraw something if there's too much going on with one diagram. Don't erase your wonderful work. Just redraw it. Get some extra paper if you need to. I redrew this without all the angles, so I'm just focusing on the segment lengths now. So let's look at DG for a moment. I want to know what DG is. That's the segment from the incenter to the edge of the triangle. That's actually going to make a right angle here. This segment over here will also make a right angle. And so will G to F. So G to E, G to D, G to F. Those are all going to be the segments that are equidistant to the sides of that triangle. Well, they're all going to have the same measure. So if I know one is 4, I know the other ones are going to be 4 as well. So I'll throw a 4 there and a 4 there. DG is simply going to be the same thing as GE. GE we have is 4. So it's going to be 4 units. BE, that one you have to think outside the box again. BE is the same length here as BD. So those two are congruent to each other. BE and BD, same length. They're both going to be 11. So I'm going to mark 11 there. And while I don't need to, I could also look at that 20 and by extension, mark another 20 along the side length EC. Those are both going to be the same. And I don't have these two, which I'm probably likely going to be able to solve for if I wanted to. But let's look at the question first. I want to know BG. BG is this length right here. Well, that ends up being the hypotenuse of a triangle. If I pull that triangle out, I have the following. I'm solving for x. X is the hypotenuse in that triangle. So we're going to set that up, and we're going to say a squared plus b squared equals c squared. BG ends up being the hypotenuse, so we'll say 11 squared plus 4 squared is equal to x squared. Add those two squared terms up, and then take the square root, and you'll have your answer. That's 137. Square root that 137, and you'll get about 11.7 for the length of BG. And our last diagram, we want to know GC. So GC is down here. So it was important to know these two down here so we could figure out this length here. So even though I didn't ask for GF, we're still going to need it to be able to solve for this hypotenuse. Or we could put the 20 there and use that right triangle as well. Both are going to be congruent triangles. So our triangle is going to look more like this. Once again, I'm solving for the hypotenuse in that triangle. That's going to be a very similar setup to answer our letter H here. So it's going to be a squared plus b squared equals c squared. We'll say 4 squared plus 20 squared equals x squared. Try to solve that, see what you get. (416), take the square root of that one number. You'll get about 20.396. I'll round that up to 20.4. X, so my length for GC is going to be about 20.4. There you have it, guys. I'll leave that work up here for a second if you need to write any of that down. A lot to break up in this problem here, but you should have enough skills now to be able to do any problems involving angle bisectors and incenters. Thank you for watching so much. I appreciate it.